Hey everybody, I'm Alessio Spagnoletti and I'll present the work on which my collaborators and I worked on. The ideas behind the project are multiples. The first one is to exploit the efficiency of generative AI models in learning the characteristics of data distributions. Then these models can be used to sample new images in a fast way, so at low cost. And we can also leverage these models to inject prior information into restoration algorithms. And the idea is to try to build a framework that uses the diffusion models and adapt these techniques to deal with astronomical images. So, a general and brief overview on diffusion models is the following. This is taken from the Song and Ehrman paper on 2019. And we have the general idea of diffusion models. So we have a distribution, we have some samples, some training images that can be slowly degraded to, to become just pure white noise. And then the idea is to go in the opposite direction. So from pure noise, we can sample an image that should be on the manifold of the training set. And the point is to learn the score function that governs the reverse process. So we can guide the reverse process through an observation Y, that in our case is the convolved image, for example, of a galaxy. So we have the X0 that we want to reconstruct. We have an operator A that, for example, is a convolution, or maybe it can be an inpainting or whatever linear operator we can think of. And the idea is to exploit the base rule to try to split in two parts, so in a prior and in a so-called likelihood term, our reverse SDE. The DPS algorithm tries to approximate the likelihood term by exploiting the same score function as theta we learned during the training process. In our specific case, so our model, what we want to do is to train a diffusion model on images that come from cosmological galaxy formation simulations. These simulations don't present any degradation, obviously, so the idea is to learn a distribution that is mm, close to the actual one, the one we expect to have if we didn't have any problems with the observations. And then using this model, we want to define a specific operator A, that is the composition of a convolution and a preprocessing. And this operator should then be reversed to get from the observation the actual image when applied to real observations. A first result is done is a test made on simulations. So we have, for example, the true galaxy here. We can think about this galaxy as if it was observed by the HSC telescope. So we can put it at a specific redshift. We can apply the PSF. And what we try to do on the left is to reconstruct it using our tailored trained model. And we can see that the residual is just the background that is added during the simulation, but the core, the central part of the galaxy is exactly the same. And we can also move to an actual test in which we take a real galaxy observed by the HSC telescope. We can take as ground truth the Hubble Space Telescope version, which has a higher definition. And we can see on the left the HSC observation that presents a lot of noise, a lot of convolution. And in the middle, we can see the result of a single diffusion step, while we can also compute more samples and compute a mean and a variance to understand better, to average the stochasticity that is present in the model itself. And we can see that the result, both the single shot and the posterior mean, is very close to what the HST actually observes. We also try to quantify the hallucinations, and the idea is to use the variance as the pixel-wise variance, and maybe we can average the pixel-wise variance in the central part of the galaxies, and this gives us a number. This number can be used to assess how much we are uncertain about the reconstruction, so how much the prior is injecting, how much information is injecting, and we do define this variance ratio that as the signal-to-noise ratio decreases, increases, and we can see indeed, for example, these images that when we add more noise, like in this case, the signal to noise is very low, the reconstruction quality is lower. And indeed, this means that our number, our variance mean, is actually positively correlated to the noise that we have, the noise that we inject. And thus, when this number is high, we are quite uncertain about the reconstruction. Thank you.